this session is being recorded, and we're going to cover the first three sections. And in these three sections, a kind of gentle introduction to graphs and level curves of functions of multivariables, right? So we're kind of revisiting some ideas, but now we're going to be looking at functions, not just one variable, but two or three. Okay, so the first thing that we're going to revisit is the idea of the domain. Okay, and before we start looking at the examples that you guys have in front of you, let's just think about a simple function that we are very familiar with. Okay, let's say I have a quadratic function, y is equal to x squared. Okay, do you remember how to determine the domain of such function? So I see y is equal to x squared. What is the domain of this function? Do you remember the general notion of domain and range? So I'm going to give you a second to think about it. So I see Sergey says R, everything, right? So all values, all real numbers. So the domain, there's a couple of ways to write it. In this case, that would be from negative infinity to infinity. That's one way to write it. Or you can write it as this blackboard R. That's what we call that letter with double-sided bar over here. Okay, so here's your domain for this function. What about range? What's the range of this function? Let me mark the domain with red. Okay, one way to think about a domain is all values of x that I can plug in into this um, function, y is equal to x squared. Well, we can square anything. Okay, what about the range? Do you guys see what the range is? Okay, so yeah, the range is from 0 to infinity. So now the range is different, right? So how do I write that? Okay, I'm going to write it as including 0 to infinity, right? Because 0 squared can be there, that's fine. And then another notation for this would be r plus, okay? Just denoting the positive real values. I'm going to mark this with green. So my output, right, is only positive values. So that's your basic idea of what domain and range is for a function of one variable. Okay, so domain is part of R. So is range. Range is part of R. But now we're going to take this idea and apply it for functions that are in three spaces, right? So three spaces, which means what? We have more than one variable. So our domains should look also differently, okay? So let's go ahead and take a look at this first example that I have in front of you. It says find the domain of each function, and I will also want to go ahead and graph it. So now I have this function f of x y, x over y. Okay, so what we don't want to happen, we don't want y to be 0, right? That's pretty clear from here. We don't want that to happen. We don't want to have division by 0. But what does that mean in the context of this problem? That means we need to exclude the entire what, x-axis, right? Y is equal to 0. We need to exclude the entire x-axis from our domain. So our domain is going to look like what? It's the plane except all of the points on the x-axis. Okay, that we're going to exclude. So I'm going to mark this with red. We're going to exclude this. And with green, I'm going to mark the actual domain. Okay. All right. So, and let me go ahead and make a note here. We're excluding the x-axis. Okay. We're excluding all points x0, right? They need to go. We need to exclude those. Everything else is okay. All right. So what is the domain then? It's all points where the y coordinate is not 0. Okay. So domain would be all points x, y, so that y is not 0. X can be 0. Okay, but y cannot be 0. Okay, and then you can think about it as what does it mean for the graph of this function? There's asymptotic behavior, right? Asymptotic behavior around the x-axis. So you can think about it now. You have a surface, right? We don't have a curve. The surface will have asymptotic behavior, so it will be going to infinity very quickly, right? So imagine, maybe take a piece of paper and bend it and just shoot it up to infinity. Okay, that's what the behavior of a function of two variables will look like around those curves where we have division by 0, right? So this is our problematic spot, the entire x-axis. Okay, so that's the big difference that might take some time for you to process, right? Because we're so used to our domain just being a part of R, but now we're going into higher dimensions. Okay, so take a look at this example real quick. Take a couple of seconds. Do you guys have any questions, or does this make sense, what we just discussed? No questions? Okay. All right, then let's go ahead and do the rest of these problems. Okay, let's see, what is the next problem? This one says f of x of y is 1 over x squared minus y squared. Okay, same type of analysis, right? We need to figure it out the values of now x and y so that we don't have division by 0. Okay, so this would be x squared minus y squared is not equal to 0. We don't want that to happen. Okay, so x squared not equal to y squared. And here we have to be careful. This means what? X is not equal to y, and x is not equal to negative y. Okay, there are two cases here to consider. All right, so we can't forget about that negative. So what does that look like? Okay, so now we need to decide which part of R2 we need to exclude. X is equal to Y. That's our identity line, right? So this is the line that goes up to the right through the origin at the 45-degree angle. Okay, that's one line we're going to be excluding. Okay, that's gone. And then the second line is y, x is equal to negative y. So that's this line right here. Okay, that also needs to be excluded. So anything in between, that's fine. So let me go ahead and shade the domain in green. Okay, which means there is a surface above these pieces, above or below, depending on, well, everything, well, yeah, depending on which values of x and y we pick. Some of them will be positive, some of them will be negative, but we have a surface in these areas that are highlighted in green. Where we have the lines in red, that's where we have asymptotic behavior, right? Okay, division by 0. When if you remember what division by 0 looks like graphically for a function of one variable, right? We have some sort of asymptote. Same idea here, except now we have a surface. Okay, so now we're going to exclude what? We're going to exclude all points such that x is equal to plus or minus y, right? Okay, those are the points that we need to get rid of. Okay, how's this example? Any questions? All good, guys? No questions? All right. Okay, then let's keep going. Let's take a look at the following example, and maybe you can help me out with this one. Okay, I have f of x is equal to natural log of x squared minus y. Okay, so now I don't have the division by 0. I don't need to worry about it here. But I do have a logarithmic function, right? So natural log of this expression x squared minus y. What are the restrictions? Okay, meaning that what do we need to remember about the log function to find the domain of this function? What do you guys think? For which values? Okay, so we can't take the natural log of 0. That's true. What else? That's not all of it. Natural log of 0 is undefined. Okay, but what else? Yes, the argument of the log function needs to be strictly greater than 0. So we're going to take the expression inside x squared minus y and set it to strictly greater than 0. Okay, so this goes back to knowing basic properties of our fundamental functions, right? So log is one of them. Okay, x squared minus y, that has to be greater than 0. So this is x squared greater than y. Okay, and now we need to think about what that looks like in R2. Okay, so here's our plane. Greater than, that means we will have a shaded line, right? So the line is not going to be included. So this is going to be our parabola. Okay, so notice how this parabola splits the plane in two regions, right? So above the parabola and below. One of those regions is the domain, okay? Except now we need to decide which one, okay? What do you guys think? How should we decide which part of this graph is the domain, okay? Think about how do we find values of x and y so that x squared is greater than y, okay? So is it the upper part or is it the lower part?
Shouldn't the
So
lower part
Corey,
be shaded?
okay, so I have two answers. Corey thinks it's above, and then Michael, you say it's the lower one. Okay, Michael, explain why it's the lower one. What's your explanation?
Because the graph x squared is greater than y. So let's say x squared at 2 is 4. It would have to be greater than all the values of y under.
Okay, so you're picking which values you're picking for x and y?
Let's say x is 2, so then that would be
Uh-huh.
4. And then y is, let's say, uh, anything below that.
Right. Okay, so one thing that you could pick is just a point in either one of these parts, right? So let's pick a point here. I'm going to pick a point over here. This point should work. Whatever you want to call it. So let's say 2, 0, right? Okay, that's a point in on the x-axis. Let's go ahead and check it. Is this statement true? 2 squared greater than 0. Is that true? Yes, it's true, right? You guys agree that's true? 4 is greater than 0. That's true. Okay, let's pick something over here. Let's pick something over here. So what is this point? Let's say this one is 0, 3. Is this true? 0 squared greater than 3. Is that statement true? No, this is false. This is how you can check. Okay, so the domain is indeed the bottom part. Okay, and all you need to do, just pick one point. That should work. Okay, now I'm glad that somebody said, oh, it's the above part. because by intuition you might be saying, no, the inequality is greater than, right? And I get that answer all the time. Okay, got to be careful here. It's x that's greater than y, right? So x squared greater than y. Okay, so we need to really think about it carefully, and then if not sure, just pick some points here. Well, and you can pick anything you want. Okay, let's pick something that's not necessarily on the x-axis. Okay, so let's say I pick let's say -1 4, so somewhere over here, this point -1 4. Okay, so is this statement true? -1 squared, is that greater than 4? No, that's also false. Okay, so that's how you can check if you've picked the correct region. All right, so in this case, stuff in green, that's going to be our domain. Let me mark stuff in red. In red, we're going to cover the actual line that's not in the domain. Okay, and then everything else here, that's where there's no surface, right? Okay, there's no function that sits above or below this piece right here. And then there is asymptotic behavior, okay, right around the curve, the actual parabola. That's where we'll have asymptotic behavior for the surface. Okay. All right, let's do one more. This should give you a good idea of how to deal with domains for functions of two variables. Okay, this one says 1 over square root of x squared plus y squared minus 25. Okay, what do we want this expression to be? I have 1 over square root of stuff, right? So let me write down that stuff. That would be x squared plus y squared minus 25. What do we want this expression to be for this function to make sense, right? What do you guys think? Or one way to think about it, what do you not want it to be, right?
Zero.
We don't want it to be 0, okay? We don't want it to be 0, but because we also have a square root, we need to make sure it's also positive, right? So this needs to be greater than 0. Okay, here we have two things to be concerned about: division by 0 and the radical, right? The square root. Okay, so to make sure that we have real valued numbers, we're not dealing with complex values, we need to have this expression to be greater than 0. Okay, what does that look like? This is x squared plus y squared greater than 25. Okay, so let's sketch it. X squared plus y squared greater than 25. I'm talking about a circle that's centered at the origin, right? With radius 5. Okay. So once again, I have my plane split up in two regions. Inside the circle and then outside the circle. Okay. What do you guys think? What's the domain? Which part will be the domain?
The outside.
The outside, okay. How do we know? Which point did you pick?
I picked 0, 0, and 6, 0.
Okay, so 0, 0 works. If we pick 0, 0, then 0 squared plus 0 squared greater than 25, that's false, right? Okay, so that's one way to show that the inside is not going to work. Or we can just pick something here. Okay, so let's say this point right here is 6, 0. Okay, so 60, 6 squared plus 0 squared, that's greater than 25. Yes, 36 is greater than 25. That's true. Okay, good. So our stuff that we're going to get rid of, okay, the line itself, that's not good. And then everything inside, that's we're going to exclude that from the domain, right? So let me make a note. This is exclude from the domain. And the domain is everything outside, so that one I'm going to mark in green. Okay, everything outside of this circle, not including the circumference of the circle, right? Okay, that's going to be our domain. Okay, so let me project all of these solutions. So you see what we're doing here. We're analytically finding the domain and then we're sketching it. Okay, so this is a really good problem. I put it a lot on the quiz. I put it sometimes on a test, and there's many things that I could ask you, right? So I could use exponential functions, trig functions, a combination of functions, right? Um, so this is a good time to revisit those fundamentals from pre-calculus. Okay, I'll give you a moment to review this again, and if there are no questions, we can move on to the next topic. We're good? Okay. All right. So then the next thing that we're going to discuss is level curves for surfaces. Okay. So what are level curves? Level curves are used to visualize higher dimensional surfaces when we can't really graph them. So something like a surface, a four-dimensional surface, we can't really visualize it. But level curves are helpful in that sense that they can give us an idea how the surface grows, right? Or how it behaves if we can just do these projections of intersections of the surface and the plane. So let me go ahead and just kind of give you a brief picture of what I'm talking about. Let's say we're dealing with a cone. Okay, so this picture is not going to go with the problem that I'm about to discuss, but just a general idea of what level curves look like. So let's say we have a cone, okay, and I'm going to cut this cone with planes. Okay, so if I cut this cone with a plane here, with a horizontal plane, then the cross section is going to be a circle, right? And then I can cut it again with a plane that sits lower. Now I'm going to have a smaller circle and so forth. And now what I'm going to do, I'm just going to go ahead and project these circles onto my plane and sketch them here again. So you can see how there's many circles that I can get. And I would mark these curves with the value of the plane that I'm cutting my surface with. So for example, let's say this plane was right here, z is equal to 1, and this one is z is equal to 2. Okay, so then I would mark my curves right here with these values, z is equal to 1, and this curve right here represents z is equal to 2, and so forth. Okay, so what this gives us the idea of how our plane is, well, how our surface is growing, okay, without actually graphing the surface itself. And Wolfram Alpha, if you haven't played around with Wolfram Alpha, is an excellent free tool that lets you see these curves and the surfaces themselves. So we're going to talk about how to construct these by hand. But my recommendation is to just go to Wolfram Alpha after the lecture and just plug in 3D plot of your function, and you will see nicer curves, because sometimes it's hard to visualize this with the pictures that we do by hand. Okay, so this might seem like very strange to you at the moment, but once we do a lot of problems, you will see exactly what's going on. Okay, so let's just go ahead and jump to it, and you'll see how to do these by hand and what it looks like visually. Okay, so the first one says find and sketch level curves of the following surfaces. So let's say we don't have a way to sketch this surface. Z is equal to x minus y squared. We can still get a pretty good idea of how this behaves. Okay, and the idea is that we're going to come up with a quick table of values, and these are usually up to you. Decide what these values are. So z is equal to some value. So z not just represent a set number. Okay, and then we're going to set our equation to that value. Okay, so for this particular example, I'm going to pick values of 0, 1, 2, 3, and 4. So this is me cutting this surface with z-planes. Z is equal to 0, z is equal to 1, 2, 3, and 4. Okay, and that should give me a pretty good idea of what that surface looks like. Okay, once I set these, I'm gonna get what? So this is x minus y squared is equal to 0. X minus y squared is equal to 1, and so forth. These are my level curves. Notice your level curves will be one dimension lower than your actual surface, right? So your surface, okay, is a 3 dimensions, and now your level curves are in 2 dimensions. Okay, so x minus y squared is equal to 4. That's my last level curve that I'm going to consider. And now I really just need to think about what do these look like? Okay, the first one is just x is equal to y squared. And then the second one is x is equal to y squared plus 1. X is equal to y squared plus 2, and so forth. So what my level curves look like, the parabolas, right? The parabolas that are shifted. Okay, so let's go ahead and sketch them, and we're going to sketch them in two different ways. Okay, when they're projected, this is what they're going to look like. X is equal to y squared. It's a projected curve. That's the parabola sitting right here. Okay, and then x is equal to y squared plus 1. Okay, so that's shifted 1 unit. And x is equal to y squared plus 2. That would be right here, and so forth. Okay, and I'm going to go ahead and label it. So all of these need to be labeled. So this is z is equal to 0. This curve z is equal to 1. This one is z is equal to 2. Go ahead and sketch the other two curves. I'm out of space over here, right? But you get the idea. So we sketch these curves, right? But really, what you should think about it is what would that look like in 3 space? Okay, so in 3 space, let me go ahead and make a different picture to represent these same curves. Okay, so here's my 3 space. This is y, this is x, and this is z. Okay, and now if I were to rewrite these curves in here, that's what they would look like. So my first parabola is z for z is equal to 0, so it just sits in the xy plane, right? But my second parabola, it's not only shifted 1 unit along the y-axis, but it's also 1 unit up. So it sits right here. Okay, my next parabola is shifted 1 more unit along the y-axis and then 1 unit up. Okay, so now you can kind of think about it as, oh, this is kind of showing you how this surface would look like if you fill in all this space between the curves. Okay, so maybe this picture will make a little bit more sense what these curves actually represent. Okay, when you look at the projected version and you see those z is equal to 0, you should think about it. Okay, this curve sits in the xy plane. Z is equal to 1. Oh, that one is actually 1 up. And z is equal to 2. That one is 2 units up. Okay, and then you can keep going. So the next one would be sitting over here. That's my parabola. And now we have a really good idea of what the actual surface is. Just go ahead and mentally fill in all the space between the curves and you get a surface. Okay, so let's take a look at this. Take a moment with this problem right here. Take a look at it. Let me know if conceptually everything makes sense to you guys. Okay, no questions, then let's keep going. We have a couple more examples here. Okay, let's see. The next example says z is equal to square root of this expression, x squared plus 4y squared. Okay, again, if you have a graphing utility, of course, we can just sketch it and see what that surface looks like. Okay, but we also want to develop this notion of level curves, so let's go ahead and come up with a table. So z is equal to z null. That's going to be in the left column. And for this one, I'm going to pick 0, 1, 2, and 3. Usually 3 to 4 level curves will give you a pretty good idea of what the surface looks like. Okay. And then here we're going to set our expression, right? So square root of this expression is equal to z null, and we'll see what that looks like. Okay, so 0 is equal to this. I'm just going to go ahead and square this. Okay, and then here I'm going to get 1 is equal to x squared plus 4y squared. Now here, once I square the left side, that's going to be 4. 4 is equal to x squared plus 4y squared. And then the last one is 9 is equal to x squared plus 4y squared. Okay. All right. So what do these curves look like? The first one is kind of boring. It's just the 0, 0. So the whole curve is just the point, right? Point 0, 0. Okay. So let me go ahead and mark this one. This is for z is equal to 0. Okay, one way to think about it is if I cross my surface with the xy plane, it crosses just at that one point. Okay, what about the next few? So the other ones are actually curves. Okay, 1 is equal to x squared plus 4y squared. That is an ellipse. Okay, so that's going to be an ellipse with radius longer on the x-axis. Okay, just roughly we can sketch an ellipse here. Okay, so this one I'm going to mark it as z is equal to 1. And then they're all going to be ellipses, right? It's just the radii are going to increase because we have a value on the right, well, actually on the left in this case, that's going to also increase. So all of these ellipses are sitting 1 and then 2 and then 3 units above, right? So the next curve also will be an ellipse with a larger radius. Okay, and then the same for the last one. Okay, so let me mark this one as z is equal to 2. This one is z is equal to 3. So one way you can visualize this, these ellipses sit in with at height, right? So z is equal to 0. That's just the origin. And then the first ellipse at the height of z is equal to 1. Next one is z is equal to 2, and so forth. And you can kind of visualize this object. Okay, it's not necessarily a cone that we can think of. It's a cone with elliptic base, right? Okay, so the one that I discussed over here was just a cone where the base is a circle. Okay, in this case, we have a cone with an elliptic base. All right, so what do you guys think? Any questions here? Is this clicking a little bit more? Yep. Okay. All right. I think we have one more problem to discuss. Okay. Let's take a look at this problem here. Z is equal to square root of 25 minus x squared minus y squared. Okay. Now let's see. What do we need to do here? First thing first, let's go ahead and discuss the domain real quick. What is the domain of this function? So we just briefly talked about the domain on the previous page, right? So how do we find domain of this function? Any idea?
Would it be all the x values inside a circle with a radius of 5, centered at the origin?
Okay, so how did you get that, Sarah?
I set the whatever's inside the square root of 25 minus x squared minus y squared to be greater than 0.
Okay,
And
good.
then I moved the x squared and the y squared over to the other side so they'd be positive and graph the resulting circle.
Good. So 25 is greater than or equal to x squared plus y squared, right? And you can visualize it as everything inside the circle, including the circumference, right? Okay, so let me mark our domain here. Okay, so this is radius 5 at the origin. So all of the points inside the circle are good. Okay, that should give you an idea of what values you should pick for for your values of z. Okay, so let's go ahead and set up our table, and then we'll pick some values. And sometimes you can pick values that are convenient. Okay, so z null, and then I'm going to set my z null is equal to this expression. Now I already see that expression here I'm going to get with the square root, right? So we're going to square things. So what I'm going to do, I'm going to pick square roots of values. So then my expressions will be a little bit nicer. So I'm going to pick 0, and then I'm going to pick square root of 5, square root of 10, and square root of 15. Okay, now remember, we want to get the idea of what this looks like, right? So we want to see the pattern. So I encourage you to pick numbers that work out nicely. Okay, so now I'm going to set this up. So the first one is going to be 0 is equal to 25 minus x squared minus y squared. Okay. And then here I'm going to get 5 is equal to 25 minus x squared minus y squared. And then so forth, right? 10 is equal to this expression, and then 15. Okay, so these are my level curves. Okay, so let's go ahead and sketch them and see what the pattern is going to look like here. Okay, so let me simplify these. The first one will be what? This is x squared plus y squared is equal to 25. And now we're going to get smaller radius, right? So x squared plus y squared. 25 minus 5, that's going to be 20. Okay, and you can see how the pattern here is a little bit different than maybe what we expected. Okay, x squared plus y squared is equal to 15, and then x squared plus y squared is equal to 10. Okay, so our level curves actually become with smaller radius, right, as we pick larger values of z. Okay, so let's go ahead and graph this. Okay, our largest circle, these are all circles, right? So let's go ahead and mark them. These are all circles. Okay, our largest radius level curve is for z is equal to 0. Okay, so and that would be radius 5. Okay, that's z is equal to 0, and that would be 5 here. Okay, and now our radii are becoming smaller, so root 20, whatever that is, right? Okay, that's becoming smaller. This is z is equal to root 5. Okay, and then the next circle has the radius of root 15, so that's also smaller. This is z is equal to root 10. Okay, and then we get the last one that we've graphed is root 10 for the radius, and for z value that's root 15. That's z is equal to root 15. Okay. All right. So now you can see how you can visualize these circles, right? And now as we get up in height, the circles have smaller radius. Okay. All right. What do you guys think? Any questions here? Is this all good? All good? Okay, let's go ahead and see if I can find Wolfram Alpha. Let's go ahead and do Wolfram Alpha. Oops. Let's go over here, and we're gonna show you how we're going to plot the first one. Okay, so let's go to our first example. Z is equal to x minus y squared. Okay, so that would be 3D plot, 3D plot, and I'm just going to type in my function. Okay, so my function was x minus y squared. That's my very first function that we've discussed. Okay, Wolfram Alpha is really nice about reading math, even though it might be not typed in correctly, so it will kind of guess what it is that you want to type in. So, and now here we can see what the actual plot is, right? So x minus y squared, that's the surface. That we kind of got an idea of what that looks like with our level curves. And here they color code. Okay, so this is what they call contour plot or contour lines. Okay, we call them level curves. That's exactly the same thing. So this will give you a quick way to check if you've done this correctly. Okay, So a free tool, it's very useful. And if you want to check your work with Wolfram Alpha, you absolutely can. That's completely fine. Okay. All right. So level curves. What do you guys think? Any questions? Is this okay? Here are 3 problems that we've discussed. So in this section, we talked about graphing domain and graphing and interpreting level curves. Okay, if there are no questions, let's go ahead and keep going. We're going to talk about limits and continuity of functions, so limits and continuities, and then we'll also talk about partial derivatives if we have enough time. Okay, so limits and continuity, that's another section that's kind of revisited in Calculus 1, except now we're talking about functions of 2 variables, right? So let's go ahead and do some limits, okay? And this section shouldn't be too complicated, all right? Computing the limits. Okay, the first thing that we want to look is limits where we have no issues as far as, all of these values are in the domain, so no concerns for the function. So if I were to evaluate a limit of a function of 2 variables, I could just plug in the numbers and see what happens. Okay, so for this one, I'm going to evaluate it by plugging in the corresponding values. So this is 4 times negative 3 squared minus 3 squared. Okay. 4 times 9 minus 9. The limit is 27. Okay. So this function is a polynomial function, doesn't have any discontinuities, no concerns. We can plug in any number and compute the limit. Okay. Let's take a look at the next function. Here we have a combination of things, right? We have a trig function. We also have division by y. I'm looking at where my point is going. It's going to 0 pi. There's no problem here because x is going to 0, but I don't have x. I don't have x in the denominator. I have y. So division by pi is no problem, right? And then sine and cosine are defined for all real values. So by just doing a quick analysis of this function, I say, yeah, okay, we can just evaluate it as is. No issues here. So what do we get? This is going to be cosine of 0 times pi, and then plus sine of 0 times pi divided by 2 pi. Okay, sine of 0, that's 0, cosine of 0, that's 1, so the answer is 1 over 2 pi. Okay, all right, and then the last function of this type, okay, what do I have here? I have natural log of square root of x, y. So here the concern could be if the expression under the radical was less than 0, right? Or equal to. No concern here. I have e squared and 4. The product of these two is positive, so I can just evaluate this expression as is. Okay, so this would be natural log of square root of what? E squared times 4. Okay, and what is this? So this would be natural log of 2e. Okay, and you can just keep it as is. We don't need to approximate it. All right, so this is an example of computing a limit for the cases where there's no discontinuity, there's nothing to worry about. We just plug in numbers and get a value. Okay. Now, let's take a look at limits that are a little bit more involved. Okay, so we call them limits at boundary points. And we say boundary points, why? Because now we have restrictions of on the domain, right? And maybe we want to evaluate that function, or the limit, we want to find the limit of the function on the boundaries. So on the one of the points that's not in the domain. Okay, so how do we deal with that? Okay, so we could look at the domain of this function and say, what is the domain? The domain here is all values that don't make the denominator 0, right? So it's x minus 3y not equal to 0. Okay, but what does it mean graphically? So graphically, we're excluding this line right here, right? So let me make this red just to stay consistent. Okay, this line has to go. The domain is everything below the line and above the line. Okay, so what if we still want to compute this limit? Because the limit might still exist, right? So if you remember from calculus 1, we could have function undefined at certain values, but the limit still exists. Well, let's see how we deal with this. Let's go ahead and just plug these values in. So 3 for x, 1 for y. We're going to get 9 minus 7 times 3 times 1 plus 12 times 1, right? Over 3 minus 3 times 1. So we're going to get 0 over 0. Okay, this is an indeterminate form. Now, your first thought might be, okay, we're going to use L'Hopital rule, right? Well, we're not going to use L'Hopital rule here. We don't know how to differentiate functions with two variables, right? Okay, so that's not how we're going to approach this problem. But even though your first thought might be, okay, 0 over 0, L'Hopital rule, not going to apply here. Okay, this is the case that we call removable discontinuity. And we've done problems like that a long time ago in Calculus 1. Removable discontinuity. We approach it by factoring things. Okay, so if I factor my function, and I can factor that quadratic, okay, you'll see what's going to happen. This is x minus 3y over x minus 3y. Oh, just kidding. That other one is x minus 4y. Okay, on the bottom we still have x minus 3y. And notice what happens. This is the removable discontinuity. Okay, that expression cancels out. And now we're left with x minus 4y, which we can evaluate at these points. Okay, so now the limit is just 3 minus 4 times 1, which is negative 1. So the limit does exist, okay, because we have removable discontinuity at that point. Okay, so take a look at this problem. Okay, this is revisiting old ideas from Calculus 1, but now we just combine it with the fact that we're dealing with a function of two variables, right? So our domain is more than just one point. We have a whole line. That's not going to work, but we do have a removable discontinuity case here for a function of two variables. Okay. All right, take a look at this solution. Let me know if you have any questions. I'll give you a minute to process. All right, if there are no questions, let's keep going. Okay, similar problem. Limit as xy goes to negative 1, 1 of this rational expression. Okay, again, let me go ahead and make the domain here just get used to this idea of thinking about a function as a whole, right? So what is the domain here? The domain is everything but this line, x is equal to negative y. So we're going to exclude that. Okay, that has to go. Everything else is okay. So you could have asymptotic behavior right around this line, right? Okay. So if we plug in negative 1, 1, we're going to get 0 over 0. Okay. So now we need to see if we can factor this. Okay. So limit as x, y goes to negative 1, 1. I'm going to try and factor my expression on the top. So I'm going to set it up like this. It's 2x and then x over here. And I need to have 3y. So I need to figure out what my y values are, right? So you can kind of predict that this expression will be the same as the one of the factors on the top. So x plus y goes here, and then figure out the rest. We need negative 3y squared. So this term should be negative 3y, and you can check that the middle term also works out to be negative xy. Okay, so that's our factorization. We have removable discontinuity, that's gone. So now we can just evaluate this limit for 2x minus 3y. What do we get? 2 times negative 1 minus 3 times 1, and we get the answer of negative 5. Okay, all right. Let's see, one more problem of this type. Okay, and then we'll talk about continuity of functions. Okay, so what do we have here? We have an expression on top, square root of x plus y minus 3. And then on the bottom, we have x plus y minus 9. The limit of this function as x goes to 4, 5. Again, you can check that if you plug in your values, we're going to get 0 over 0. Okay. The domain of this function is a little more complicated because there are a couple of things that we need to keep in mind. First, we don't want the denominator to be 0, but also we'll need to make sure x plus y is greater than or equal to 0, right? So that's the radical expression. So we're not going to get involved with the domain for this function, but we can still solve the limit here. Okay, so 0 over 0. That means I should have a removable discontinuity. Okay, so there's a couple of things here you could do. One thing you could do is try and factor in. So that's what I'm going to do now. I'm going to factor now the denominator. Okay, so limit as xy goes to 4, 5. On top, I'm not changing anything. On the bottom, even though it doesn't look like it, it is difference of squares. Which squares? Square root of x plus y minus 3, and then square root of x plus y plus 3. Okay, and now we can remove this factor here. So what is the limit? It's 1 on top, and we can evaluate our expression on the bottom. So 4 plus 5, square root of that, plus 3. So we get 3 plus 3 on the bottom. So this is 1 over 6. Okay, that's one way you could do it. We could also, another trick to remember, multiply by the conjugate. So another way to do it is multiply by this expression, x plus y, square root of that, plus 3. And of course, we multiply it on top and on the bottom. Okay, and you will see that you're going to get exactly the same answer. Okay, so whichever method is more intuitive to you, whichever one you feel more comfortable with, that's the one that you should go with. Okay, All right, so let's see limits at boundary points. Any questions here? All good? All right, then let's keep going with the next concept for limits. How do we show that the limit does not exist? Okay, let me remind you a little bit from Calculus 1. Let's say we had the following situation. Let me give you a function and see if you can explain to me why the limit does not exist. Okay, so let's say my function looks as follows. Okay, I have one branch that looks like this, and then the other branch that looks like this. Okay, let me go ahead and mark these values with some numbers. So this one is 1, and let's say this one is 3. Okay, let's talk about it real quick. What is the limit of my function as x approaches 2 from the right? Okay, see if somebody can answer that. What is the limit of this function as we're approaching 2 from the right?
1.
Okay, what is the limit of this function as we're approaching 2 from the left?
3.
Okay, what is the limit of f of x as x goes to 2?
Does not exist.
Why?
Because for a limit to exist, they need to be 14 from the same side.
Very good. So for the limit to exist, they need to be approaching the same value from 2 sides, right? So here we had 2 sides, okay? So we had from the right going to my value of x and then from the left, okay? That's it. Only 2 sides to check because our domain is just R, right? So there's nothing else to check, okay? But now what do we do when we have infinitely many ways to get to the point? Now remember, our domain now is the entire plane, right? So now one way to think about it is your domain is the whole plane, right? Or parts of it, okay? How many ways are there to get to a certain point? Let's say even just to the origin, okay? How many directions are there? There are infinitely many. I can come through this curve, or I can come through this curve, or I can just come through this straight line. There are infinitely many ways to now approach a point of interest because we're not restricted to just x and y axis. It's the whole plane. There's uncountably many of those. So to show that the limit does not exist is a little bit more challenging. In this case, what we need to do, we need to show that the limit is different for 2 different lines. And once I go through a couple of these problems, you'll see exactly what's going on. Okay, let me go ahead and remove this because I need some space here to make solutions. Okay. So these 2 problems say show that the limit does not exist. Okay, I am telling you it doesn't exist. Okay, it's a fact. It doesn't exist. We just need to show that it doesn't. All right. How do we do it? I'm looking at my point. Which point is it that I'm interested in? 0, 0. Okay. How many lines are there that go through the origin? Infinitely many of them. There's lots and lots of lines. So I'm going to pick easy lines that go through the origin, okay, that cover that point, to see if I can find 2 different lines that produce 2 different limits for me. Okay, so and you'll see what's going on here. So let's imagine our R2. Okay, here's my R2. I'm going to pick the first line, line 1. I'm going to pick y is equal to x, so my identity function, right? Okay, so let me go ahead and make this line right here. This is my first line. If I'm approaching the origin on this line, either from here or here, it doesn't matter. What does my function look like? How does it behave? That's what we're really trying to figure it out. Okay, if y is equal to x, what is the limit? Now the limit of xy going to 0, 0. Y and x are the same, so I'm just going to rewrite everything in terms of x. Okay, so that would be 4x times x over 3x squared plus x squared. So that's 4x squared over 4x squared. Okay, that's just one. Okay, so one way to think about it is the following. Whatever the surface looks like, if I just follow the surface along the line y is equal to x, as I get closer and closer to 0, I'm going to be sitting at the 1 unit above the plane, right? This is z is equal to 1. Okay, that's what my limit is. Okay, so let me repeat it again. If I follow my surface along this line, y is equal to x. As I get closer to the origin, I'm going to end up at 1. So that's kind of like the height of where I'm going to be literally physically sitting, right? Okay. Now, let's think about another line. So line number 2, okay? I'm going to follow a surface along a different line. I'm going to pick y is equal to negative x, okay? So if I do exactly the same thing, so walk on my surface, except now I'm following this line, also contains the origin, right? And that's important. What's going to happen? Where will I end up? Okay, and what is the limit? Now x is equal to negative y, so the limit is going to look like what? X is equal to negative 1, 4x negative x on top. On the bottom, we still get 4x squared. So the limit is negative 1. Completely different number. So one way to think about it, if I follow my surface along the other line, the purple line, I'm going to end up in a different spot. That means the limit does not exist. Okay, so two different values, the limit does not exist. All right, so take a look at this problem right here. Take a minute to kind of wrap your head around it. Let me know if there are any questions. No questions? All right, let's do one more problem of this type. Okay, same idea. I have an expression that gives me 0 over 0 if I plug in my point, right? Okay, so I need to show that the limit does not exist. Okay, and this might take you some time to kind of find those lines. My first line I'm going to pick is going to be just x is equal to 0. Okay, or the y-axis. Now notice every time I pick my lines, I need to make sure that the point of interest is actually on the line. So 0, 0 is on that line. Okay, what happens if I compute this limit? Limit as xy goes to 0, 0. On x is equal to 0, that's going to be y to the fourth over y to the fourth, which is 1. Okay. Now I'm going to pick a line y is equal to 0. See what happens here. Limit as x, y goes to 0, 0. If y is equal to 0, we get negative 2x squared over x squared, negative 2. Okay. Negative 2 is not equal to 1. I found two directions for my surface, that if I come from two different directions, I end up at two different points. Okay, that's it. That's enough for me to show that there is no limit. Okay, now let me give you an example. Let's say you come up with two lines and these two lines produce the same limit. We cannot conclude that the limit exists. You can have 55 lines that produce the limit, and all it takes to have one other line that gives you a different limit. Okay, so that's why it's actually kind of difficult to show that the limit exists. It's a lot easier to show that the limit does not exist. Okay, you just got to kind of go through your lines and see which two produce different values. All right, but that's a common mistake that I see sometimes. I say show that the limit does not exist. Students pick 2 or 3 lines, end up with the same limit, and then they conclude that that is the limit. That is not true. Okay, keep looking. Keep looking for that one line that will give you a different answer. Okay. All right, so we're gonna keep going because I do want to cover partial derivatives. Okay, so let's talk about continuity of functions. So that's the last part of this section. Determine the points where the functions are continuous. Okay, so let's take a look at a couple of different simple functions. The first one is a polynomial function. There's no problem here. This function is continuous everywhere. Okay, so this is continuous on R2. Okay, another way of saying all ordered pairs x, y. Okay, think about which values of x and y I can plug in and have this function being defined, right? Anything. It's a polynomial function. Those polynomial functions are nice and easy to deal with. Okay, so this function is continuous everywhere. Okay, so everywhere on R2. Okay, what about the second function? 2xy on top, no problem there. On the bottom, we have x squared minus y. Okay, x squared minus y, we don't want this equal to 0, right? We don't want this to be equal to 0. Okay. So what are we excluding? We're excluding our parabola. Okay, so just this curve right here. Everything else is okay. Okay, so what is our conclusion here? Where's the function continuous? It's continuous everywhere that it's defined in this case, right? Okay, so it's defined for all values. So for all values except the values on this parabola. So this is continuous for all points x, y, so that x squared is not equal to y. Okay, so everywhere on the domain it's continuous. Now let's take a look at the next problem. That one is a little bit more complicated. It's a little bit more involved. So this is a continuity of a function that's piecewise defined. Okay, so let me rewrite it in a piecewise notation. So f of xy, what is it? It's this rational expression that we actually just worked with a few minutes ago, right? Oh, this should be to the fourth power plus x squared. Okay, that is if x and y are not both 0, right? Okay, and then it's 0 otherwise. 0 if x, y is equal to 0, 0. Okay, that's my piecewise defined function. Where is this function continuous? So now we have to be a little bit more careful because we need to consider continuity at a point. So what is continuity at the point? And that is something we've covered in Calculus 1. So it might have been a long time since you talked about that concept. So let me go ahead and remind you. So what is the continuity at a point? In our case, it's going to be an ordered pair, right? Okay. So first of all, the function needs to be defined at that point. Okay, so f needs to be defined at that point. Before we even talk about continuity, we need to make sure we have a value, right, for that function. F defined at this point. Okay, second condition, the limit as x, y goes to this point must exist. Okay. And then not only that, the limit also needs to be the value of the function. So limit is also equal to the value of the function at that point. So these are the three conditions that we need to satisfy. Okay, and we've done these conditions for just a function of one variable, right? So we only had just that one x. In this case, we have an ordered pair, x null, y null. All right, so now let's go ahead and see which conditions are satisfied for 0, 0, right? We don't have any problems for points if it's not the origin, okay? There's no problems there, all right? The function is continuous for all values, not the origin, no problem, okay? What about the origin? Is it defined? Yes, okay? It is definitely defined. We just define it right here. It's equal to 0. What about the limit? We just showed that the limit does not exist. We showed it in problem 2 over here. Okay, so this condition is the one that's not satisfied. Now, if it was satisfied, let's say the limit did exist, we would also need to check the third part. Does that limit also equal to the value of the function? Okay, but in this case, we don't even need to go into the last part. So that means f is continuous everywhere except the origin, except 0, 0. Okay, it is discontinuous at that point, and the reason is being that there's this asymptotic behavior that goes all over the place. Your surface goes in different directions if you come from different paths, right? So that's your discontinuity. Okay, so this type of problem also may be a little bit counterintuitive and might take you some time to really wrap your head around this idea of a limit not existent because there are different values coming from different directions. Okay, so let me go ahead and project everything that we've done for this page right here. Take a look at it. Let me know if there is anything you would like to discuss before we finish up our lecture with partial derivatives. Okay, then let's keep going we're going to discuss partial derivatives, and for this part I only want to focus on computations, and we'll because we're running out of time a little bit, but I do want you guys to know how to compute partial derivatives, and we'll talk a little bit more about interpretation of what that actually means. What do partial derivatives means? So notation for partial derivatives. Okay, so what's your notation? Let's say we want to take a partial derivative of f with respect to x. So I'm going to use this curly d df dx. This represents partial of f with respect to x. Okay, and then we can do the same thing for y, right? So for y, that would be partial of f with respect to y. Sometimes your textbook will use f subscript x. That's the same thing, so that would be df dx, or they will use f subscript y, that would be df dy. Feel free to use whichever notation you like. Okay, so how do we compute partial derivatives? We're going to talk about computations, and then next time we'll talk about what that actually means. So partial of f with respect to x. How do I compute this? We're going to pretend that the other variable, so my other variable in this case is y, is a constant. Okay, in a sense, think about it this way. I want to know the change only in the x direction. I don't care about the change in the y direction. I'm going to fix that y. Y is now a constant. And when I see rate of change of my function only with respect to x. So now y, anywhere you see y, that's a number. Okay, that's the easiest way to think about it as computing partial derivatives. So now I'm going to differentiate this function pretending that y is a number. Okay, so I'm going to get what? Let's see, power rule here, right? So that's going to be 12 x cubed y. Okay, and minus what? X is the variable, y is the number, so that would be 2y, and plus what? X is a variable, y is the number, so this is just 5y cubed. Okay, that's my partial with respect to x, and then partial with respect to y. Now I'm going to hold x as the constant, y is the variable. I'm going to go back to my original function. Okay, the derivative of 3x to the fourth y with respect to y, that's just a constant, right? So 3x to the fourth, okay, minus what happens here? This is 2x, and then plus y is the constant, 15. I'm sorry, y is the variable, x is the constant, so that's 15x y squared. Okay, so take a look at these expressions. Does that make sense? All good? Okay, I'm gonna go ahead and find second derivative. Okay, let's go ahead and find the second derivative with respect to x. How does that look like? D squared f dx squared, that's the notation. Okay, also you will see textbook using f subscript xx. Okay, same idea though. I'm going to differentiate this function, my first derivative with respect to x. Y is still treated as a constant. Okay, so now I get 36x squared y. Negative 2y prime, that's gone, right? This becomes 0 because now that's just a constant, no variable. Okay, so that's minus 0. And then what about 5y cubed? That's also 0. The derivative of that with respect to x is 0. Okay, so my second derivative with respect to x is just going to be 36xy squared. Okay, and then let's compute second derivative with respect to y. Okay, what do we get here? Okay, 3x to the fourth with respect to y, that's 0. Same for 2x, that's also 0. What happens here? Okay, now here we don't get 0, we get 30xy. Okay, so that's my second derivative for each of the variables. What do you guys think? Does this make sense? Any questions? Are you guys with me? Is this okay? Yep. Okay. All right. Let's keep going then with more complicated functions. Same idea. I want to find the first, just the first partial derivative. So let's go ahead and find just the first partial derivatives for this function that looks like a ratio here, right? Okay. So let's do this one carefully. df dx. Okay. So quotient rule. So prime of e to the negative x times x squared plus y squared minus e to the negative x times x squared plus y squared prime with respect to x. And then we divide this by the square in the denominator. Okay, so what do we get here? We get, let me move it over here. So this would be negative e to the negative x times this expression minus e to the negative x, and then what happens inside? With respect to x, this expression becomes 2x, right? The derivative of y squared is 0, since that's a constant, okay? And we divide this by x squared plus y squared squared, okay? So we can factor out e to the negative x, or negative e to the negative x, and we get a little bit cleaner expression, but nothing can be canceled out, which is fine. So this is our derivative with respect to x. Okay, let's go ahead and do the partial with respect to y. Okay, now I can use the same setup, the initial setup, except now I'm going to differentiate it with respect to y. E to the negative x with respect to y, that's 0. Okay, so that term is gone, minus e to the negative x. And then what's the derivative of this expression with respect to y? That's going to be 2y. Okay, so we end up with negative e to the negative x times 2y divide by x squared plus y squared quantity squared. Okay. So what do you guys think so far? Computing partial derivatives, just just actual computations. Does that make sense? Yeah. Okay. Then we have one more problem, and then we're done for today. It says find the second order partial derivatives. Okay. We can do that. I have cosine of the product x y squared. Okay, let's deal with x first. So df dx. Okay, what is that? First, we need to deal with cosine function. The derivative of cosine is negative sine of xy squared. And now we deal with chain rule, right? Okay, times the derivative of the inside with respect to x. That would be y squared. Okay, so my first partial with respect to x would be negative y squared times sine x y squared. Now, because we're asked to find second order partial derivatives, okay, we're going to compute the second one, d squared f dx squared. Now we're going to take this expression and differentiate it again, okay? Y is a constant, okay? So we can just treat it as that. That's a constant, negative y squared, okay? Derivative of sine is cosine, okay, cosine of the same argument. And now we need to do the times the derivative of the inside with respect to x. So that would be y squared again. So we get negative y to the fourth cosine of the same argument, x y squared. Okay, let's do the same steps for y, df dy. Okay, derivative of cosine is negative sine. Derivative of the argument with respect to y. What is it? Can somebody tell me?
2xy.
Good. So 2xy. Okay, so my first derivative with respect to y looks like what? Negative 2xy times sine xy squared. Okay, very good. Now we're one step away from being finished. The second derivative, the second partial with respect to y. Okay, now we got to be careful because we have a product of two functions of y, right? So we have to be very careful. We got to use product rule. Okay, so that would be the derivative of negative 2xy with respect to y times sine of xy squared plus negative 2xy times the derivative of sine xy squared. Oops, square goes with the y. Okay, prime. Okay, I'm using the product rule, so we have to be very careful here. Okay, the derivative of negative 2xy with respect to y, that would be negative 2x sine of xy squared. Okay, what happens here? Okay, this stays as is, negative 2xy. The derivative of sine, that's cosine. And then the derivative of the inside with respect to y, that would be 2xy, right? Okay, so if you want, you can combine these two terms right here. That would be negative 4x squared y squared, right? Simplify it just a little bit, okay? So we need to be able to comfortably and quickly compute these derivatives. So the first few problems for this particular section will just ask you to compute these derivatives and just kind of get used to this notion of partial derivatives and how to compute them. Now start thinking about it. What if you have the partial derivatives? How do you find the function, right? So undoing this partial differentiation, that's the fun part, okay? That's the part that's like, oh, maybe that is not as straightforward as just computing the derivative. So that's what I'm gonna let you think on for now, okay? Start thinking about this process of undoing partial derivatives and how it's related to integration. Okay. All right, I'm gonna stop right here right now because we're really close to being done. So thank you all for coming. I will stay online once I stop the recording for anybody who has any questions about the class.